Hello everyone. So let's wait for 3 to 4 minutes and after that we will start. Hi.
Hey, good evening, Amit.
Yeah, good evening. So my PPT is visible, my audio, video, everything is okay?
Yeah,
Yeah,
so
okay.
far so
Thank you.
good.
Thank you.
So will this be the last session?
Yes, yes. Okay, so we have waited enough. So good evening everyone. I welcome you all to the live session number 12 for the week 12. So for the NPTEL course, Hydrogen Energy Production, Storage, Transportation and Safety. So the course instructor is Professor Pratibha Sharma from IIT Bombay and I'm this course TA Amit Kumar Sharma. So as of now we have covered 11 weeks and today is the last class for week 12. So you all aware that every week we are having live session. So the purpose of this session to show you about the previous year's assignment question and go through the previous week's class videos, notes, so that you can have a quick summary and in a sense a doubt clearing session. So let's start with today's class. So as of now, we have covered various aspects of hydrogen production, storage, transportation, about refueling station. So today we will go through the sensing and safety and something about global and Indian status. So the question number one is the greatest number of hydrogen related accident occur in option A laboratories, fueling station, power plant, onboard hydrogen storage in vehicles. If you have gone through
Lab,
the
sir. A.
class
A,
videos,
sir.
then okay. So we have one answer, option A. Anybody else? Okay. So the correct answer is A. So the greatest number of hydrogen related accidents occur in laboratories during the experimentation and testing. Okay. So we have some data regarding the incident related to the hydrogen. So on the left side, you can see here human error or equipment failure. So here you can see the accidents are almost 38.3% in laboratories, almost 11% in fueling station, 9% in commercial facilities, 7.98% in power plant, and so on. So the maximum incidents are happening in laboratories. And the reason for these incidents are human error or equipment failure. Either the person who is doing experiment, he is doing some mistakes, or the equipment that are used in the laboratories, so they are having some kind of malfunction or failure. Due to that, number of incidents are happening in the laboratories. Also, if we see, so the reason, so maximum is due to the piping, fitting, and walls. Okay, so either the piping rupture or fitting or wall breakdown. So almost 32% incidents are due to this only, because you know the hydrogen is very light gas. Okay, and you are having various kind of walls, pipings, fittings. So suppose you are having your experimental setup at X location, and maybe the storage is at Y location. So from X to Y you are having a piping, and maybe the due to the location and due to the space constraint, this pipe is either like zigzag type, or there will be so many connection fittings and all. So there are so points where this leakage can happen. Okay, so either the wall breakdown, fitting breakdown, or piping rupture. So most of the incidents are due to this only. Other reasons are like hydrogen storage equipment in cylinder outlet damage due to valves, regulators. Okay, so almost 12.66% in vehicle and fueling station, then the safety systems, ventilation systems, and all. So these are the data regarding the incidents related to hydrogen. So there's an element of risk. Okay, so the acceptable level of safety is represented by the R equal to P multiplied by C. So probability multiplied by the consequences due to the incident, also the cost associated. So here we are having the predictive techniques. We can assess the risk, then the quantitative risk assessment QRA, and the probabilistic risk assessment PRA. So risk management is identification, assessment, and prioritization of risks, coordinated and economical use of resources to minimize, monitor, and control the probability and impact of catastrophic events. So basically, because we are handling the hydrogen, so we need to consider all the aspect of risk management. So identification, assessment, and prioritization of risk, then the coordinated and economical use of resources to minimize, monitor, and control the probability and impact of catastrophic events. So these are the important element for the risk management. So in past, so there are some incidents, the Hindenburg disaster. So on 6 May 1937, New Jersey. So fire with explosion, so killing 36 people. Outer shell and pent of airship was flammable and could have been ignited. Electrical spark, electrostatic discharge was also there. So you can see this. So 36 people killed in this incident. So it is a major incident. Due to this, uh, the hydrogen use was very limited. Okay, but the study on this incident later on resulted that maybe the fire was due to the outer shell and pent of the airship was flammable, not only due to hydrogen. Okay, also due to the electrostatic discharge. So there can be many reasons for the initial ignition that caused this incident. Then the hydrogen vapor cloud explosion. So on 23 October 1989, Houston polyethylene plant. Then it was extensive damage, 22 lives and 100 injuries. So in this release of process gas during maintenance, several flaws with installation was recorded. No hazard assessment, inadequate safe distance, lack of permit of for maintenance, design error with building ventilation. So these were the reason for this incident. Then the compressed hydrogen tank rupture in 1991, Frankfurt. So almost 100-meter cube tank at 45 bar burst. Due to this shock wave and missile lead to a lot of damage to the industrial plant, welding in metallic cracks from inside to outside region lead finally to improvements in the hydrogen tank safety. After this incident, there were major improvements in the compressed hydrogen tanks. So we have covered in our previous classes type 1, type 2, type 3, and type 4 kind of tanks. So we have covered this slide already. So also if you see the hydrogen embrittlement and facilities fatigue, so equipment failure almost 35.78%, then human error. Okay, so to avoid the catastrophic events, improved technologies, infrastructure and strategies played the major role. So in any incident, you can see the property damage was up to 42%. Now there are some important properties for gaseous hydrogen associated with accident. Okay, because we know that if we are storing the hydrogen in gaseous form, so we need to aware of all the properties of that hydrogen. So based on that, we can design our system. So it's a very important slide. So the hydrogen is colorless, odorless, not detected by the human sense, potential asphyxiant. So buoyancy is a measure, you can say a good factor. It leak, moves upward, very light gas, safe level below LFL, not accumulate in unconfined spaces. So if your space is unconfined, then it will not accumulate due to the buoyancy effect. So as compared to hydrocarbon, they're not so buoyant. And in the Flixborg 1974, Brucefield 2005, so there were more strong and fire explosion due to hydrocarbons. If you compare the parameters, so if you see the density at STP, hydrogen 0.089, natural gas 0.717. Okay, the minimum ignition energy in air, so C is millijoule, so only 0.017. So 0.017 millijoule is required for hydrogen as compared to natural gas 0.31. So it's very low. Flammability limit, so 4 to 75%. Wide limit, and it's at NTP. If you change the operating condition, so this limit will also change. So for natural gas is only 5 to 15%. And the LHV value, it's huge, almost 120 for hydrogen, 50 for natural gas. And the boiling point, ignition temperature, 574, 650. The burning velocity is also huge, almost 3 times, 2.65 to 3.25, and 0.38 only for natural gas. So these parameters are very important. So if you are having the liquid hydrogen, then the situation is different, because in that case the density is higher, So the diffusivity of hydrogen is also very good. You can see here 0.63 centimeter square per second as compared methane only 0.20. So it's also a good property. So if you are having hydrogen leakage, so that will diffuse very faster. So the chances of in in case of unconfined space, the chances of explosion is less. Low viscosity and small size of hydrogen, so it leads to high flow rate and leaks. So also the burn in clean atmosphere with an invisible flame. Wide flammability limit. It also expand with the temperature. The burning velocity depends on temperature, pressure, and composition. More difficult or confine or arrest flame. Explosion confinement difficult to achieve in detonation where velocity is 3 order of magnitude higher. We have covered here. So escaped hydrogen very easily ignited. Ignition source avoided. Hydrogen in a electrical insulator flow or agitation of gaseous hydrogen or liquid hydrogen may generate static charge. So grounded is necessary. So regarding the liquid hydrogen, so the properties of liquid hydrogen. So stay close to ground will move horizontally or downward. So it's liquid, so it will stay close to ground either horizontally or downward. And if you are using the pipe, because you are it's liquid, so in the pipe or if it's vents and walls, they can get blocked by the accumulation of ice. Then it can develop to the excessive pressure. So due to that, there can be small rupture in the vessel and a jet release of hydrogen. Okay, jet type release, and there mechanical failure potential BLEV. So the volume decrease because we know if we are doing the condensation, the volume will decrease. It's create a vacuum. So with vacuum, then some air will be thrown in there. With air, there will be moisture. So the solidified air gets stored with liquid hydrogen. Okay, then its concentration increases during repeated refilling or precipitation producing explosive mixture with hydrogen. So to avoid this system worm during maintenance when frozen material regasify resulting in high pressure or explosive mixture. Then the storage vessel and positive pressure to avoid any air inflow. So you will maintain positive pressure so that there will be no air inflow and producing flammable mixture. Liquid hydrogen vessels to be periodically warmed and purged to keep accumulated oxygen level less than 2%. So we need to have periodically warmed and purged to keep the oxygen level less than 2%. Then if we talk about the expansion ratio, because we are converting the gaseous hydrogen into liquid hydrogen, so there will be huge volume change. So volume of liquid hydrogen expands during liquid to gaseous. And another volume increase occur when gaseous hydrogen warm from NBP to NTP. So here you can see the final volume is 847 times the initial volume. And also the final pressure is 177 times. So due to this, there should be always a relief valve to release this high pressure. And the expansion ratio of gaseous hydrogen at 25 megapascal to atmospheric pressure is 1 ratio to 40. So also the hydrogen embrittlement is a measure. We have covered this about in our previous classes. So it's a major issue. So it can deteriorate the mechanical properties of metal, and the selection of appropriate metal is an important part of hydrogen safety. So the material that you are choosing for your vessel and for the storage, so there should be no embrittlement. The material should be metallurgically stable. Phase change in the crystalline structure do not occur with time or repeated thermal cycling. So in summary, we can say hydrogen not more safer or dangerous than other fuel. It is different. So every flammable fuel, hydrocarbon and all, so they have their own properties. So they have their handling. They're also dangerous. Similar like that, hydrogen is also dangerous and also like based on the properties, we have to choose the condition. So it is not more safer or dangerous than other fuel. It is different. For safe use of hydrogen, the underlying safety measure and possible hazards should be known. So for the safe use, you have to be aware of all the properties for the gaseous, liquid hydrogen, and the requirement of the material to avoid the embrittlement. Okay. So which among the following is physiological hydrogen hazard? Vapor cloud explosion, embrittlement, fire, asphyxiation.
Asphyxiation.
Okay, we have an answer option D. So answer is already here. So it's asphyxiation. Answer is D. So type of hydrogen hazards are divided into three categories: physiological, physical and chemical. In physiological, so asphyxiation, overpressure, thermal burns and cryogenic burns, physical embrittlement, environmental, internal and hydrogen reactions, and the chemical rupture explosion, fire, and we see vapor cloud explosion. So what is the meaning of this asphyxiation?
So asphyxiation is basically hydrogen is replacing the oxygen, and it is when it is more than 95% of the replaced oxygen, then there is a problem of breathing. Oxygen
Yes.
deficiency is there.
So if you're in a confined space and there is no ventilation, so hydrogen can replace the oxygen, displace the hydrogen can displace the oxygen, and the concentration of oxygen will decrease, and you will okay, and there will be the case of asphyxiation. Yeah, please mute yourself. One of you is unmuted, and we can hear the background noise. Okay. Then there are some terms. So explosion, if there is a rapid release of hydrogen and there is ignition, then the rapid release and the pressure rise will be there. And deflagration, flame front moves through a flammable mixture in form of subsonic wave with respect to the unburned mixture. And detonation, flame front coupled to a shock wave propagates through a detonable mixture in the form of a supersonic wave with respect to the unburned mixture. It propagates 1,000 times faster than the deflagration. In the BLEV, sudden release of a large mass of pressurized liquid into the atmosphere. If flammable ignites, forming a nearly spherical burning cloud or fireball. UVC and CVCE, confined or unconfined vapor cloud explosion. Flash fire, very dilute or very concentrated fuel mixture, but in flammability limit. Flame travels in cloud at low speed and very less pressure increase. So some important definition. Which among the following is not related to the material properties causing hydrogen hazards? Linear blistering, damage or of carbon, fire, boiling liquid, expanding vapor explosion, BLEVE, embrittlement.
It's a damage of carbon fiber, option B.
I think it will be fiber, na? Instead of fire.
Yes.
Yeah.
Fiber, yes. Damage of carbon fiber.
So anybody else? We have one answer.
It is boiling liquid expansion and vapor explosion.
Okay, we have another answer, a different one. So let's once again go through the question. The question is about which among the following is not related to the material properties causing hydrogen hazards. So it should be not connected with the material.
Boiling liquid
Yes.
expansion.
Because if
Yeah,
you see the
BLEV.
so the correct answer should be the C. Okay, because we have seen that BLEV is sudden release of large mass of pressurized liquid into the atmosphere. If flammable ignites, forming a nearly spherical burning cloud or fireball. So there is no connection with the material at all. Okay, it's a leakage of a large mass of pressurized liquid into the atmosphere. Embrittlement, we know, is a metal properties, then also the blistering and also the damage of carbon fiber. So correct answer is option C. So if you go through the cause of hazards, then it's due to the material properties related or handling system related. So under the metal properties related, here comes linear blistering in the pressure vessel, hydrogen permeation, embrittlement, the damage to the carbon fibers, resistance to the fire and high temperature, and the property changes at lower temperature. So these things comes under the material properties. And if you see the handling aspect, then the BLEV, boiling liquid expanding vapor explosion, then the gas is hydrogen leakage, liquid hydrogen release, hydrogen jet fire, the temperature variation, thermal radiation, delayed ignition, and explosion. So these are the two major causes of hazard which are connected with the handling system or metal properties related system. If you see the gases hydrogen hazards, then the release is connected with three uh, like immediate ignition. Either there can immediate ignition, then delayed ignition, or rupture of vessel. So release can be due to three reasons: immediate ignition, delayed ignition, or after release there can be two options like immediate ignition, delayed ignition, and rupture of vessel. So these two, if there is hydrogen air flammable mixture and ignition source. So factors to assess the appropriate consequences. So the characteristics of release like pressure. So when there is a release, then what is the pressure, low or high? Then the size, the buoyancy driven or not. Then the space, confined or unconfined. Then the source, any potential ignition source present or not present. Then the ignition, it was immediate or delayed. Then the external aggression, not release, but external aggression like thermal, mechanical or storage vessels, rupture or burst. So these are the factor you need to assess appropriately. So the gas is hydrogen release in the unconfined spaces, then release with immediate ignition. So it's unconfined spaces. So a jet fire or flash fire, flame length and associated relative heat flux, a thermal effect. So what is the difference between jet fire and flash fire? Anybody?
Jet fire means there is a continuous small jet fire is there, and flash fire means once fire is done and then it got extinguished like that.
Okay, anybody else?
Jet fire means the suddenly that pressurized gas will release, and if there is any fire, then what will due to the high pressure and density, so all of the gases will not be catch fire, so it will I mean propagate along with the fire. So that is the jet fire and flash fire when a vapor makes, I mean the gaseous mixture with along with the oxygen, sufficient oxygen, with high volume, and is there any fire? So that is flash fire.
Yeah, nice. Good explanation. So yeah, jet fire. So if like there's a high pressurized vessel, you can say here. So here hydrogen is there and a small rupture here and there's a leakage. So the hydrogen is coming out at high pressure. Okay, so the size of this leak is very small. So here you can see, and also there's air outside, then the ignition source is there, so there will be like a jet fire. Okay, so all the hydrogen is not coming in contact with the oxidation or air, but in the flash fire, a large volume lightly coming in contact with the like oxygen, air, and the ignition source, and there is sudden full fire. There's a flash fire. It's like a jet. You can see like a jet. So it's jet fire. So release with delayed ignition. So if the ignition of release is delayed, a flammable cloud will be formed before the ignition, and the ignition will induce a deflagration. So UVC unconfined vapor cloud explosion with overpressure effects infecting potential surrounding people and installation. Level of congestion, like pressure presence of obstacles of the site, will be an escalating factor. And deflagration and to detonation transition is possible in confined and or obstruct situation. So if we have the confined space and there is a release of gaseous hydrogen, so a confined space can be more concurrently or a container hosting process or hydrogen storage, garages, parking, tunnels, accumulation. So the hazardous that can be included in this is formation of flammable mixture, burn if ignited with hazardous pressure, and thermal effects will be there. And the destruction of structure, enclosure or building by pressure peaking phenomena, or pressure exceeding enclosure or building structure strength limit in case of sufficiently high hydrogen release rate, high release flow rate, small enclosure, small size of vents during unignited or ignited release, and asphyxiation due to the displacement of oxygen. Then the hydrogen buildup. So hydrogen release in a confined space will accumulate according to ventilation rate, concentration level, and distribution are different. So it depends on the ventilation. If there is no ventilation, then hydrogen concentration will depend on the release duration. Long duration release can reach up to 100%. Natural ventilation is driven by the buoyancy effect. So way of hydrogen buildup mitigation is the case of accidental release in confined spaces. The mechanical ventilation is driven by fans or other mechanical devices limiting hydrogen concentration inside a confined space, used when natural ventilation is not possible or not sufficient to reach safety targets. In the venting panels, so we can set up on the roof of the container. Flames are directed upwards. Aerial overpressure at ground level is very limited and container deformation is limited. Efficient mitigation means limiting the effect of an explosion in a confined space. So these are the things we can do. So if the burst of a pressurized vessel, then the burst of a pressurized vessel is a physical explosion with rapid expansion, generating overpressure wave in addition to the fragments. So it can occur at normal operating pressure, working pressure due to degradation with time of the pressurized volume, corrosion, fatigue, embrittlement. These are the reason for this. The mechanical impact on the pressurized volume and also the bursting pressure due to overfilling. So there is a like limit and you are doing the overfilling. Then the inadequate pressure relief. There is no pressure relief. So it can lead to internal explosion or reaction and fire aggression. Liquid hydrogen hazards are immediate ignition, delayed ignition, flash evaporation, partial evaporation, BLEV, and the cryogenic boiling pool formation. So immediate ignition, so there will be high pressure jet or pressure effect due to ignition. Delayed ignition, so flow horizontally or downwards after immediate release of liquid hydrogen, condensation of atmospheric humidity, making it visible and more dense. Because its temperature is very low, so the atmospheric humidity will condense. So high expansion ratio larger than the cloud induced by gaseous hydrogen release. So we have seen that the expansion ratio is very high, almost 800 times. Intensity and distance of effect, if the pressure is low or release diameter So there can be jet, a rainout phenomena. So formation of hydrogen droplets falling on the ground and inducing a hydrogen pool can be observed. So the cryogenic hydrogen pool vaporization. So a hydrogen liquid spillage can induce a pool. Liquid hydrogen will vaporize and form a flammable cloud with a significant volume. And the wind condition have a significant impact on the propagation and the dispersion of the cloud. And the UVC, so it's a cold reactive hydrogen air cloud formed, ignited, and flame could interact with the obstacles, vaporizer, pipe break, vegetation, possibly leading to flame acceleration and even to a deflagration to detonation transition in the worst case scenario. About BLEV, so liquid which is stored at temperature above its saturation temperature at atmospheric pressure, some of the liquid will flash to vapor, resulting in the generation of overpressure. Ignition of the released contents produce a large fireball, which can determine the hazard range. So there will be large fireball in the source, so it can be is a BLEV. So the normally liquid hydrogen vessels have pressure relief valves. Failure blockage of the system could lead to a BLEV. If there is a failure or blockage of this relief valve, it can lead to a BLEV, or fire attack could raise pressure and lead to a BLEV with fireball due to inadequate venting of pressure. It's very important to have a pressure relief valve. Which phenomena among the following will occur on immediate ignition of gaseous hydrogen released in unconfined space? So unconfined vapor cloud explosion, BLEV, jet fire, cryogenic pool formation.
It is jet fire.
Yes. Anybody else?
I think, sir, A, vapor cloud explosion.
With jet fire, unconfined, confined, then it could be the cloud.
So the question is immediate ignition. Okay. In unconfined space. It's unconfined, not confined, and there's immediate ignition.
And it is gaseous,
Yeah,
not
it's
liquid.
gaseous.
Yeah.
Yeah. So the best option matching is the jet fire. Okay, because BLEV they are like delayed. There is a formation of, you can say, cloud and all. Okay.
BLEV is related to the liquid.
Liquid, yeah. Liquid and
Cryogenic also liquid, then unconfined also.
yeah. So it's liquid and it's flash to vapor, resulting in large overpressure. Okay. So the correct answer is C, jet fire. Which among the following is advanced quantitative risk assessment model? Event tree, discrete dynamic event tree, fault tree, parts count. So which among these is the advanced quantitative risk assessment model?
Dynamic event tree.
So we have one answer, option B, discrete dynamic event tree. So correct answer is the option B, discrete dynamic event tree. So this event tree, fault tree and parts count are like conventional, or you can say the old quantitative risk assessment models, and the advanced one is the discrete dynamic event tree. So for the hydrogen risk assessment, we can have numerical analysis, theoretical models, and experimental data. Based on these, we can do the hydrogen risk assessment, and we can also follow the industrial practices. So it's the good one because we know that industries are using hydrogen for a long time. So these practices are very important. So the outcomes of hydrogen risk assessment is identification of key risk drivers. So what are the measure? You can say points, factors, parameters that are the drivers for the risk. And the establishment of mitigation strategy, and you need to come up with a strategy to mitigate the risk, and the prevention of potential accident. So these 3 points you need to consider under the hydrogen risk assessment. Then by combining these three, we come up with regulation, codes, and standards. Okay. So based on these three, we have some regulation, codes, and standard that we have to follow so that we can avoid the any accident. So if we talk about the QRA, so the quantitative risk assessment, so this is the chart. It start with the selecting risk matrices, then the tolerability criteria, then describing comprehensively hydrogen system, then the identification of potential condition to cause damage, then the characterization of outcome resulting into accident. So this is the flow. So traditional models are event tree, fault tree, and parts count. Okay. So for the QRA, so extended QRA, Bayesian network, and the advanced QRA, dynamic probabilistic safety assessment. So traditional these three, and the advanced version are advanced QRA, dynamic probabilistic safety assessment. So it's include discrete dynamic event tree and the event sequence diagrams and the sampling and simulation based QRA and PSA models. What is the expansion ratio of a leak of gaseous hydrogen stored at 25 megapascal to a atmospheric pressure? 1 to 240, 1 to 04, 1 to 847, 1 to 402.
C, 847.
So we have one answer C. Anybody else think about it?
It is C.
The question is it's given 25 megapascal. Try to think more. So it's not at the NTP. We're talking about a particular pressure 25 megapascal, then to atmospheric pressure.
It is 240.
Yes, nice. So the correct answer is option A, 1 to 240. Okay. So because it is stored at 25 megapascal, Then it's coming to atmospheric pressure, and it's 240. So we have covered it here. So the expansion ratio of gaseous hydrogen at 25 megapascal to atmospheric pressure is 240, and the expansion ratio of volume of liquid hydrogen expands during liquid to gaseous hydrogen, and another volume increase occurs when gas hydrogen warms from NB to NTP. So it is 847, and liquid to the gaseous, NBP to NTP. The percentage reduction of oxygen level in confined space due to release of hydrogen can increase human pulse rate.
It's a 15 to 19% oxygen.
Okay. Do you have any reasoning?
Means normally we require 20.9%. So below that there is a SY section, means there is a low concentration of oxygen. So human cannot breathe. No less oxygen.
Okay. You say reduction of oxygen level. So it is not showing you the exact number of how much oxygen is there. So it's a reduction of oxygen level.
Okay. Okay.
Okay, so the correct answer is option B. So 12 to 15% reduction of oxygen level in confined space due to release of hydrogen can increase human pulse rate. And greater than 20% and equal to 20% can lead to what? So that can danger to the life. Okay. So for the pulse rate, it's 12 to 15% reduction. So according to the National Hydrogen Energy Mission, the space of hydrogen blended with CNG will be utilized as a fuel for transportation. 2, 10, 15 or 18%.
It is 18%.
Yes, so the answer is 18%. So let's see something about the National Hydrogen Energy Mission. So it was launched by our Honorable Prime Minister on 75th Independence Day on 15th August 2021. So it's aimed to meet India's climate target and making India a green hydrogen hub. So because we know that green hydrogen is vital to making a quantum leap towards achieving energy independence by 2047. Okay. So why only hydrogen? Because it's a clean fuel. And if we want to have energy independence with the cleaner and greener future, then we need to rely on the hydrogen and renewable energy. The major target is to produce 5 metric ton of green hydrogen and develop related renewable energy capacity. So the gray hydrogen, so 80% hydrogen blended with CNG and to be utilized as a fuel for transportation at Rajghat bus depot. And the HCNG pilot, so 50 buses are plying in Delhi using HCNG as a fuel. So 80% is the target, 18%. So the green hydrogen, so hydrogen produced using solar energy. So establishment of two solar powered HRS for demonstration of fuel cell electric vehicle at two locations, Delhi, Agra and Gujarat. Then the establishment of one pilot green hydrogen production plant to replace conventional hydrogen with green hydrogen in refinery. Then the establishment of one pilot green hydrogen production plant and its blending with CNG to be used at retail dispensing outlet in Rajasthan. Then the establishment of one pilot green hydrogen infrastructure and injection of green hydrogen in city gas distribution pipeline network. So promoting R&D, so Hydrogen Corps Fund (HCF) to fund the R&D led by oil industry with an active involvement of academic institution. So now we have National Green Hydrogen Mission. Okay. So first it was National Green Hydrogen Energy Mission. So under this now we have NGHM. So there's a green hydrogen, green ammonia policy released on 17th February 2022 by Ministry of Power, Government of India. So the hydrogen and ammonia are looked upon as a future fuels to replace fossil fuel. So the policy provides following benefits to the green hydrogen, green ammonia related stakeholders. The first, the green hydrogen ammonia manufacturers may purchase renewable power from renewable exchange or can also set up their own renewable energy capacity. So where do we use ammonia?
Fertilizer.
Yeah, in fertilizer.
So in
Fertilizer,
fertilizer. Yeah.
then methanol generation.
Yeah.
Yeah.
So what is the green ammonia?
Where the source of hydrogen would be from renewables.
Yes. So
using
the
the
hydrogen
fossil
is used for the ammonia generation. So we use the green hydrogen and make ammonia, then that's a green ammonia. So open access will be granted within 15 days of receipt of the application. Then the unconsumed renewable power can be banked with distribution company for 30 days. So there are some details about the policies. So also according to the proposal, beginning from 2023 and 2024, refineries will have to meet 10% of their hydrogen demand with green hydrogen and increase the same to 25% in next 5 years. Then the fertilizer producer will have to meet 5% of their hydrogen demand with green hydrogen, increasing the same to 20% in the next 5 years. So these are the targets. So how much percentage of refineries present hydrogen demand is supposed to be met with green hydrogen as per green hydrogen, green ammonia policy of Government of India?
It's a 10%.
It is 10%. 10%.
Yeah, so we have covered here. They have to meet 10% of their hydrogen demand with green hydrogen. So answer is A, 10%. 20% hydrogen blending with natural gas can offset carbon intensity by percent.
It's 8%, sir.
So the correct answer is it's 7%. So the 20% blending may offset carbon intensity by 7%. So the global building sector consume 30% of global final energy use. So hydrogen can be blended with natural gas 5 to 20%. Natural gas constitute 35% of global energy demand for heating. So why this only up to 20% we have considered initially? If you go through the
Because with the 20% in gas, we can use mostly use the existing infrastructure.
yes, because uh, we are having we have covered this in our previous classes in the hydrogen transportation through pipelines. So we are having like huge network all over the world for natural gas. That's also some area is newly laid and some network is very old. So we can use all the network safely without any risk up to 20%. Okay. We can also modify that and can go so like some higher limit, but as of now, we have tested up to 20% for the old natural gas pipeline. So that's why it's 5 to 20%. So 20% blending may offset carbon intensity by 7%. Negligible use of hydrogen currently. So currently we don't have negligible use, but it has huge potential. Several demonstration projects are underway. So we are also examining the blending of hydrogen gas grid. There are projects in H21 north of England. Heating demand is 100% on hydrogen. So the Korea have 15.7 megawatt of electric installed in buildings. So there's a huge potential for hydrogen. Then may not suit for all building application. Blending with natural gas for heating purpose we can use. So indirectly to heat or cool local district energy networks and supply to buildings. So hydrogen have a huge market in buildings for heating, electricity, and etc. The following properties of hydrogen are assets when safety of hydrogen is concerned. High diffusivity, low ignition energy, wide flammability limit, high flame speed.
All, sir.
Hmm?
Asset where safety
Following
of
properties
High
of hydrogen are
diffusivity.
asset.
High diffusivity.
Yes. So which one of these property is considered as a asset to the
diffusibility.
hydrogen?
First one.
Yeah, diffusivity
Yeah, it is
because
diffusivity. Yes.
so it's the diffusion rate is very high. So if there is a leakage, so it will diffuse very faster. So in like if the space is like your area is unconfined, so there is no issue with that. So high diffusivity is an asset. So low ignition energy also a risk factor, limit risk factor, high flame speed also a risk factor. Okay, so we have covered here. So diffusivity, if you consider, it's 0.63 centimeter square per second for hydrogen, methane 0.20, gasoline 0.08. Expansion ratio when liquid hydrogen leaks spills at NBP and evaporates to gaseous hydrogen at NTP is
847.
yes. So we have covered that from NBP to NTP it's 847.
So what is this NBP?
So it's normal boiling point.
Okay. So
NTP normal temperature and pressure. So It's NBP 20P 847. Which of the following is not a hydrogen-related hazard? Physiological, physical, chemical, hydrogen released in unconfined space, and absence of ignition source.
Option D.
Yes, because we know that's there. It's a chemical hazard, physical, physiological. But if there is a release of hydrogen in unconfined space and there is absence of ignition source, and due to the diffusivity, buoyancy, and all, so it's not a hazard. Among the following, which is a material-related hazard? Hydrogen embrittlement, BLEV, flash fire, fireball.
First one, embrittlement.
Ingredient.
Yes, so we know that we have covered this in our previous slides, previous weeks uh, videos also. So embrittlement is the material-related hazard. Which among the following is hydrogen handling related hazard? Hydrogen permeation, liner blistering, delayed ignition and explosion, change in properties at low temperature.
It's a liner blistering because in the storage tank.
The question is the hydrogen handling related, so it's important. So try to remember, we have covered in today's class only
Delayed ignition
the
and
material related and the handling related hazards. So it's about the handling related. So if you consider the permeation, then it is through the material. So it's not regarding handling. And the liner blistering also, it's a material. And the
delayed ignition
change
and
in, sorry?
I think delayed ignition and explosion is the handling hazard.
Yes, delayed ignition and explosion is the handling hazard, because the properties at low temperature change is also the material. So the correct answer is option C, delayed ignition and explosion. The main reason for the failure of hydrogen equipment is piping, fitting, walls rupture, electric equipment failure, safety system failure, operating temperature.
First one.
ನೆನ್ನೆಗಿಂತ ಗೆಲುವಾಗಿದ್ದಾರಮ್ಮ ಚಳಿಗೆಲ್ಲ
Yeah,
ಏನಿಲ್ಲ
please mute
ಚೆನ್ನಾಗಿ
yourself.
ಲೂಸ್
One of you
ಮೋಷನ್
is
ಆಗಿದೆ
unmuted. Chandrasekhar, please mute yourself. Okay, thank you.
ಸಾರಿ
So the main reason for the failure of hydrogen equipment is piping, fitting, walls rupture, and the electric equipment failure, safety system failure, or operating temperature.
It's a safety system failure because like failure of PRV pressure relief valve.
Okay. Anybody else?
The piping fittings all structure.
Sir, operating temperature could be the
Yeah, these can be. Yeah, these are the all. These things are mentioned here. They all are the reason. But the what
all
is
are
the main reason? The main reason for the failure, like we have tried to remember the initial slide in which we have covered the main reasons. So like one reason is having 30% weightage, other is 15%, 10% like that. So there is a main reason for the equipment
So
failure.
yeah, it will be the safety system failure.
Okay. So the correct answer is option A. Piping, fitting, and wall structure are the main reason for the failure of hydrogen equipment. So if you see the data here, so it's 30, almost 32.38% due to the piping rupture, fitting, and walls breakdown. Okay, so the storage equipment failure is 15%. If you consider the safety system, which comes under the safety system failure, it's only 7.9%. The major equipment failure is due to the piping rupture, fitting, and wall breakdown, wall rupture. Okay. So the primary reason, next question. The primary reason for the physical type hydrogen hazard is high temperature, low pressure, embrittlement, flash evaporation.
Embrittlement.
Yes, so the correct answer is embrittlement. Yeah. So physical type hydrogen hazard is the embrittlement. Which among the following is not the traditional model used for quantitative risk assessment? Event tree, fault tree, parts count, dynamic probabilistic safety assessment. We have
Option
covered
D,
this
dynamic.
already.
Last one.
Yes.
Yeah.
Dynamic probability.
So these three are the traditional one, and this is the other one. Fourth largest hydrogen consumption sector is refinery, ammonia synthesis, methanol synthesis, and DRI.
DRI.
What is the full form of DRI?
Direct reduction of iron.
Yes, nice. So the answer is DRI. So if we see the use of hydrogen, so if we consider the power to fuel, then we can have synthetic fuels, ammonia. We can have heating purpose like industrial and residential. For transport, we can have road, train, aviation, shipping, power sector, large scale energy storage, power generation, off grid power supply. We can have for space application. For industrial use, we can have for refining, ammonia, methanol, and DRI. So if we see the hydrogen refineries, so 33% demand in refineries, so 40%, 40 metric ton, million metric ton hydrogen is in 2020. 50% is met by the catalytic naphtha reforming and steam crackers, and remaining is met by either on-site production or externally sourced from merchants. So demand will increase due to growing refining activity and rising requirement for treatment till 2030. Okay. So demand will slow down after that because we will have improved efficiency of all the systems, so that will decrease the losses and we will have electrification. So 200 million metric ton CO2 emission in 2020 for meeting refining hydrogen demand. So see the emission of CO2, it's huge. That's why we are shifting towards the green hydrogen. So ways to reduce emission is integrate carbon capture utilization and storage units, CCUS, or use of low carbon electrolytic hydrogen. So the capture hydrogen from SMR is lowest cost option and policy support. So how much CO2 is emitted from the SMR process? for 1 kg of hydrogen? Try to remember our previous classes. So almost 9 kg CO2 per kg of H2. Okay. If you are using natural gas as a fuel for the SMR process. So in chemical industry, ammonia and methanol is larger, having the second and third largest demand. So the larger producer of byproduct of hydrogen used within sector or distributed elsewhere, mostly produced from fossil fuels. So H2 is the part of molecular formula of almost all chemicals. We know hydrogen is everywhere. So can we have, like, what is the hydrogen? Do we have any direct source of hydrogen in our, like, in our system, in the systems? Do we have any source of direct hydrogen on Earth?
No.
So direct source, it's also a byproduct in many petrochemical, wherein
No, my question
uh,
is like, no, my question is like, we are having the fossil fuels. So,
right,
okay, we are having like oil, we are getting it from the earth. Okay, we are having natural gas, so we can have it directly.
right.
Do we have any source of direct hydrogen available
No.
on earth?
No.
Sir, hydrogen has also been discovered in certain oil wells, basically which are gaseous. Rather than natural gas, there are also underground hydrogen sort of reservoirs.
But that is also due to some reactions only. The
Yeah.
science
So
behind that is due to some reactions only. So basically, the thing is that hydrogen is an energy carrier.
yes.
Okay, so hydrogen is energy carrier. It is not available in the direct form. So it
So
is in,
water is the
yeah, water is also have
source for
hydrogen.
yeah, store of
So yeah, so water is having hydrogen, and the for water is the key ingredient for the green hydrogen.
right,
Okay, because if you see the electrolysis, so what we are doing in that, we are just breaking the bond of water, H2O. We are
right,
breaking the bond. Okay, so hydrogen is the energy carrier. It's not available directly in its pure form, hydrogen. Okay,
true,
so yeah, so it's a molecular formula of almost all chemicals. It's a part of formula. The demand of hydrogen for primary chemicals is 57 million metric ton per year by 2030. Energy efficiency and material efficiency strategies, so it can reduce emission, reduce increasing demand, use of cleaner pathways, increase energy input and cost. Because if you are having the cleaner pathway, then it will increase the cost and also the input. Low cost renewable electricity is requirement, so the cost competitive additional buffer storage and transport cost is also important factor in this. Now the iron and steel production, so it's the fourth largest demand is DRI, and the producer of large quantities of hydrogen in mixed gas form, coke oven gas, all required hydrogen from fossil fuels. To reduce emission, use of hydrogen is key reducing agent by 2030, blending into existing process. So in the steel sector also, we are using hydrogen. So now in that sector also, green hydrogen is promoted. Okay.
Sir, DRI furnaces, there is a new approach wherein the bio CBG can be injected directly into the DRI furnaces. It will give you carbon black as a residue and release hydrogen, which will be a pure form.
Okay. Basically, you are doing the
Pyrolysis,
catalytic
pyrolysis of
reforming.
CBG or
Yeah.
methane rather.
So you are doing the methane cracking, na? Using the some catalyst and methane cracking.
Yeah, it is. So when you inject it in the DRI furnace at that temperature, that uh, decomposes the methane from, but the source is biogas, rather the compressed biogas, enriched one.
In this CBG, yeah, okay.
Right.
So CBG is also like you can consider it like methane only because as per the standard of CBG, the methane content should be more than 90%. And normally in the CBG, we have almost 94 to 95% of methane and 3 to 4% of CO2. So basically
Right.
at high temperature, it breaks. So there will be, so the methane cracking will be there. The CH4
Right.
will crack into carbon solid and to H2
Solid
hydrogen.
carbon, so it can be used
Yeah,
for any carbon black applications, and hydrogen is released, which
yeah.
is can
But it
be yeah.
requires so much of heat.
Yeah, that is anyhow there in the DRI furnaces.
Yeah,
So
yeah. Yeah, so yeah, it can be used. It can be used. Okay. Now the global projects. So the annual industrial hydrogen demand is 51 million metric ton. So only one third of the electrolytic hydrogen projects are expected to be operational by 2030. So blending pure H2 in DRI and blast furnaces is a substantial of substitute of coal and gas. So these are the projects that they are doing. Then a demonstration of projects using electrolytic hydrogen used in methanol production. Netherlands, Belgium, Sweden, they are working on this. And the demonstration project using electrolytic hydrogen for ammonia production. So USA, Denmark, Norway, Netherlands, they are having projects. Okay, so hydrogen transport. So 20% of global GHG emission, 25% total global energy demand, and 90% of energy supplied by oil products. So fuels electric vehicle reduce local air pollution. The synthetic fuel we can have methane, methanol, ammonia, liquid fuels, range of potential transport use. Electrolytic hydrogen, synthetic liquid fuels, power to liquid, and the production of low carbon synthetic fuels have significant opportunity. So basically, the use of hydrogen transport sector, it's huge potential, and these are the options. So you can see the delivery fleets require long range, cost effective where hydrogen stations exist. So in China, leads the deployment of 412 registered trucks, 100 vans outside China. FedEx and UPS they are doing in this sector. So in June 2021, 40,000 fuels electric vehicle on road. So 70% annual growth observed between 2017 2021. But now I think it has increased so much. So in rails, so we have two Alstom trains completed greater than 180,000 kilometer travel distance. Germany, Austria have started regular passenger service in 2020. UK, Netherlands are doing pilot run for fuel cell rail, while France, Italy, UK have placed orders for trains. Then in shipping, green ammonia is looked upon as 100% potential alternative to power ships by 2023. In aviation also, Airbus is exploring hydrogen-powered aircraft concept with potential of carrying 200 passengers up to a distance of 3,700 kilometers by 2035. So as per the announced place scenario, hydrogen demand in transport sector is 520 petajoules and projected to rise 15 times by 2050. So 70% cost reduction in automotive fuel cell compared to 2008. So it's important. So as we are moving forward, we are going for larger high production rates, new discoveries and R&D. So the cost of fuel cell is reducing. The 70% reduction as compared to 2008. By 2030, 1.3 million systems per year have been targeted to be manufactured, leading to 90 gigawatt annual production potential. So the potential in cost reduction, fuel cell stack, storage, refueling, and availability of infrastructure. So we need to reduce the stack cost. Storage cost is also high. To reduce it, refueling. So building we have covered. It can be used for heating, electricity, like for power. So power generation and energy storage currently negligible role, but it can change the future. So co-firing of ammonia to reduce carbon intensity in conventional coal power plant. And H2 fired gas turbines, combined cycle gas turbines. They can give flexibility with increasing shares of renewables. So it can be used for energy storage, compressed gas, ammonia, synthetic methane. Okay, to balance the hydrogen seasonal variation. So if you are producing the green hydrogen, but the demand is not that much, so you can store it for later, either in the compressed form, ammonia form. You can make synthetic methane and later you can break it. In the demonstration, so 20 megawatt hydrogen fired combined cycle gas turbine in Italy, and S2 fired gas turbine in Kobe, Japan, and the Korea 40 megawatt gas turbine with 95% hydrogen gases for 20 years. So fuel cells, we have covered it in our previous classes. So high efficiency, flexible operation, installation is rising for backup power and off-grid electricity. Japan aims at 1 gigawatt of hydrogen-based power capacity by 2030. Korea 1.5 gigawatt installed fuel cell capacity by 2022 and 115 gigawatt by 2040. Now these are the national hydrogen strategies for various countries. So as of now, we have Japan, Korea, European Union, Germany. So European Union is having 40 gigawatt of electrolysis target by 2030. And they are investing almost 4.3 billion USD by 2030. Japan 6.5 billion USD. Germany 10.3 billion USD. So now we have Canada, France, Netherlands, UK, Norway, Russia, Spain, Portugal, Czech Republic, Hungary, Chile. So these are the countries that they are having their own national hydrogen strategies and they are working so much towards the green hydrogen. Now, what are the major barriers? So the cost is a major barrier. So it's for the cost for the green hydrogen still high related to high carbon fuels. The cost of production, the transporting, converting and storing hydrogen is also high. Then the technological maturity is a barrier. Because some technologies, a low level of technology readiness and need to be proven at scale for the larger scale. So gas turbines that operate exclusively with hydrogen, maritime trade. There's only one prototype vessel that can transport liquid hydrogen. And efficiency. So there are losses of value chain, including production, transport, and conversion. and use. So we need to consider the efficiency of each part, then the overall efficiency can be considered. The sufficient renewable electricity, so electrolytic hydrogen consume close to 21,000 TWh by 2050. Almost as much electricity is produced globally today. End use sectors are electrified. A lack of sufficient renewable electricity may become a bottleneck. Also, the policy and regulatory uncertainty. So, as of now, over 140 countries have pledged to achieve net zero emissions within the coming decades. The speed with which these goals will be achieved remain uncertain. Stable long-term policy frameworks are needed to support development and deployment at scale. So, as of now, 140 countries have pledged, but how they will achieve this, what will be their policy and all, so they are still in under development stage. Now, the standards and certification. So, as we are talking about all over the world, so there should be harmonized standard required. So, it can be transported anywhere in the world. Chicken and egg problem: without demand, investment remain too risky, could lead to economic of scale, but without economies of scale, the technology remains too costly. So, there are some key points. So renewables together with energy efficiency will responsible for energy transition. So we need to have renewables, but with energy efficiency. Then only we can have a good energy transition. Hydrogen will play a key role towards climate change mitigation strategies. So 12% of final energy consumption by 2050 by green hydrogen. H2 will allow transport of renewable energy over long distance, promoting energy trade. So basically we can transport the hydrogen in form of methanol, green ammonia, liquid hydrogen and all. Okay. So in, you can say, upcoming years in Europe, Netherlands is about to become the major hydrogen importer and exporter. Okay. So for Europe actually. So Netherlands will try to import hydrogen from various other part of the globe, and that will become a gateway to the Europe, because Netherlands is having very connecting pipeline all over the Europe. So they are having like a full grid of pipeline there that is connecting major part of the Europe. So Netherlands is having huge port, so he can facilitate the import of hydrogen in form of ammonia, green methanol and all, and can transport that hydrogen to the other European countries. So that's why H2 will allow transport of renewable energy over long distance, promoting energy trade. So countries with ample renewables deployment will become major producer of green hydrogen, and India is trying to achieve this goal because we are having huge solar potential, wind potential. Okay, we are also having space, so we can become a hydrogen producer and we can also export it. So government of India is working very good under the NGHM mission, and by 2030 we will be exporting green hydrogen to other countries. So in terms of hydrogen trade, some countries will become major exporter and the business will become more competitive. Cross-border trade of hydrogen will increase. New bilateral energy relation will be established. Many countries will become exporters. Some of the countries which are energy importers like Chile, Morocco, Namibia, demand will increase from 2035. There will be huge market potential, economic competitiveness. So use of hydrogen will reduce import dependence, address price volatility, and increase resilience of the energy systems, providing flexibility and diversification. Requirement will be harmonized rules, standard and norms to increase deployment of H2 technologies and for the trade. Initial market growth could come from applications where hydrogen is the only possible solution. So way forward is ready, prepare, and need to demonstrate. So industrial processing, buses, car fleets, forklifts. So we are using hydrogen in these sectors. So gas blending, power to gas, blue to gas, light, medium, and heavy duty trucks. We are preparing and we are having some demo for these. And the need to demonstrate is marine, rail, mining, aviation, H2 heat and power, steel. They are under research. So chemical refinery remain major consumers. Transport, building, power sector all have potential to use H2 if cost of the production and utilization decreases. It's an important thing. The cost is very important part for the wide scale adoption of the hydrogen. The advantage of using hydrogen as an energy carrier include reduction in energy import, increased carbon footprint, decreased resilience of energy systems cannot be produced from renewable.
So it is reduction in energy import.
First one.
Yes, because every country is spending lot of amount, lot of rupees, or you can say lot of currency, their currency for the energy import. So advantage of using hydrogen as an energy carrier can reduce the energy import. So it because it's a cleaner fuel, so it will not increase the carbon footprint. It can be produced from renewables, so it is wrong. Decrease the resilience of the energy system, wrong. It increases. So yeah, it's all for today's class from my side, and today is the last class. So any query? Okay. So as today is our last class, so I want to have feedback from those who are present. So as you know that we have covered we have covered these areas: production, storage, transportation, about sensing and safety, refueling station, and global and Indian status. So uh, I would like to have your feedback, like because you have gone through this 12-week course, okay? You have gone through the class videos and you have gone through the live session. So briefly, you can tell me how was your experience through these live sessions and what is the benefit of this course? Because before this course and after this course, what is your change in your thinking, and what do you think that this course will benefit you in your future after this learning? So just briefly, you can share your thoughts. Okay, so maybe we can start
Good
with
afternoon. Good
yeah,
afternoon, sir. I am Dr. Sanmugam.
yes, please.
Sir, I was working in an educational institution as a lecturer with a mechanical background, having
Okay.
40 years of industrial experience.
Oh, nice.
So I was teaching mechanical subjects. So I was thinking that I can join this NTPL course. So I selected hydrogen storage and safety, this thing transportation, and as well as innovation, business plan, and as well as entrepreneurship. These two
Okay.
courses I am attending. So after attending this program, I am also acting as a project coordinator for student projects and as well as the staff projects, particularly research projects and other things. And I am helping them for the competitions also, national level competitions. So
Oh, nice.
after attending this program, so I am having some idea that hydrogen is going to be a major this thing which will change the economy of the India, not only India and the global also.
Yeah, yeah.
And moreover, this innovation and startup also started very rigorously in India, particularly after Narendra Modi has taken place. This is power.
Yes,
So
yes.
I am shortly going to Canada, sir. I
Oh,
will be
nice.
staying for about 6 months. So I thought of doing some research work in the some Canadian universities, particularly in the Calgary. I am going to stay there. Some Mount Royal University or something is there. Anyway, I'll try my level best if I can do some research in terms of this hydrogen production and as well as storage and other aspect also. And additionally also for the electrical battery advancement technologies.
Okay.
So I am some good impressions also, and particularly the madam was giving a very good lecture, and every time you are consolidating all these things and giving your feedback. Particularly this Amit Kumar Sharma, particularly your lecture was very useful because you are very patient and giving time and then explaining it. I am
Yeah,
understanding your concept very well, rather than madam also, because
yeah. Thank you.
yes, sir. Yes, sir. So I really thank you, sir. Thank you very much. And moreover, I thank other gentlemen also, Mr. Subhatra, who is also taking part in this tutorial class.
Yeah,
This
because
thing.
because we are having good discussion in every class, so it's a very important. Yeah, because whenever we have a discussion, so we can also have like doubts,
Yes,
because
sir. Yes,
one mind is only thinking in one direction. If we have multiple people involved, then we have multiple thoughts,
sir.
so we can discuss that and we can come up with the final thought actually. Yeah,
Because I was having a plan, sir, that I can learn some technology development in terms of hydrogen production, storage, and as well as
yeah,
distribution, and as well as application part also in Canada. So
yeah.
if
So I
you can know
yeah.
something about that, these things, sir, you can throw some light to me so that I can use my service, or while staying there in 6 months, I can learn something, sir. Maybe in working with the industry or some research institution, I can learn something and bring it to our India also, sir.
Yeah, yeah, nice, nice. So yeah, actually, yeah, it's a very good opportunity for you. So I wish you all the best for this. So because as you are going there, so now you are aware of every aspect of this hydrogen economy. We have
Yes, sir.
covered like every aspect from production to storage to transportation, everything. So maybe you can find with the host universities that in which technology they are working, and you
Yes,
can
sir.
also explore that and you can contribute in that and you can learn from there also and you can come to India and you can start some projects here. Yeah, actually
Okay.
it's a good opportunity. Yeah. Thank you.
Right, sir. Thank you, sir.
Yeah,
Thank you, sir.
thank you. Yeah. So next,
Yeah.
Mukesh.
Hi.
Yeah.
Yeah, hi. I'm
Hi.
Mukesh Mehbubani. I'm a chemical engineer, and I have been working in industry since 1997. So it has been now 27 years. I'm working in
Oh,
the
really?
yeah manufacturing field, and I had
Nice.
done course on energy efficiency at IIT Bombay under Mr. Professor Rangan Banerjee also, and that was
Actually, now
a very
now he is the director of IT Delhi. Actually, yeah.
yeah, I know, I know. At that time, he was in energy department
Yes.
of the IIT Bombay, and then through Aditya Birla Group, I went there. So, and when we talk about this course, this is definitely a very helpful course because the Indian government is now thinking for going for hydrogen as well as also blending with a CNG, and even in manufacturing industry also we are using so many natural gas as well as the fossil fuels also we are using other fossil fuels, so it would replace hydrogen. So by going through this course, particularly I could understand it deeply what is actually the how hydrogen can be produced and what are other ways rather than the conventional ways we know, and what are the mainly safety part of the safety part was very important because ultimately in industries safety plays a very vital role as well. As far as these problem solving sessions are concerned, so I could learn very quickly and very deeply through these problem session solving sessions. In 2 hours we could learn so many things, not only particular problems or MCQs, rather than even theories also, theory and particular, and just so in 2 hours I could learn, we can say, the entire week's sessions. So this was thank to you and your team also. So it was a very helping for me, and even it also helped me to solve our tutorials also during this session. Yeah.
Yeah, nice. Thank you. Thank you. So I wish you all the best for future endeavors. So I hope this course will help you in your future research and your future, like if you are currently you are in like
Yeah.
manufacturing, so maybe you will also move, will have some projects regarding hydrogen in your sector. So I hope you can use this knowledge there also. Yeah,
Yes. Yes. Yeah. Thank you.
yeah. Thank you. Thank you. Yeah, next. Who
Okay,
wants
namaskar,
to?
Amit.
Yeah, hi,
This is
hi.
Chandrasekhar. Okay.
Namaskar. Yeah.
Okay, namaskar. First of all, it came to me, this particular course. I heard about this course a couple of years back. Somehow I could not pursue, and since I started pursuing the using hydrogen was one of my dream for last maybe 15 years or so. I've
Oh,
been in
nice,
this is my
nice.
I've been in auto industry for last 28 years. This is my 28th year in auto industry, and
Oh, nice.
mainly I was been into engine and vehicle emissions, mainly about emissions and mainly working on fuel efficiency.
That's why you
Fuel
are very
efficiency has
interested in
been my
hydrogen because it's the greener fuel and most clean fuel
correct,
actually. Yeah.
correct,
Yeah.
right. Yeah, and if you look at the CO2 perspective, and wherein I've been part of the CO2 scenarios, if you know the regulations in India, the Bharat star labeling and star ratings and other things. I've been involved with it right from its formulations way back from 2007, 2008 onwards. So
Okay.
there has been always my question: why can't we use hydrogen,
Yeah.
especially in the small engines, not the big engines? See, if you look at
Yeah.
today, everybody are looking at fuel cells. Fuel cells for India is a very cost intensive. It's very difficult from the affordability perspective. Maybe
Yeah. Right. Right.
2 decades down the line, yes, it is possible. That is nothing is impossible. But if you
Yeah,
look
but
at
right now,
the
yeah, right now the
scenario,
cost is a major
right,
barrier. Yeah.
right. And if you look at that perspective from the life cycle assessment, and that is when I say ISO 14064, 66162, 6364, it also talks about life cycle assessment and circular economy. Key point here is circular economy. And if you see the amount of small engines what we have for various applications, I'm trying to see how it can be used. Yes, it is from the commercial standpoint or anything, it is negative, but we need to explore how we can make it possible. That has been my wish.
Okay.
And since I started doing my PhD also, let me see how it goes. That's where it is.
Oh,
And
really? You are doing PhD. Nice.
yes, correct.
Okay.
Now I'm doing my PhD. So since I'm doing my PhD also got registered, and this was my topic is using hydrogen, green hydrogen, technically green hydrogen for small engines.
Oh,
And
nice,
this
nice.
small engines is not easy. It is not a straight line. Let me see how
So,
it goes.
what
I'll
do you
keep you
mean by
updated.
small engine? Like, how much power they will produce? Small engine means
It is less than 4 kilowatt.
less than 4 kilowatt. Okay.
Less than 4 kilowatt. And if I had to say, it is less than 300 cc engines.
Okay. Okay.
Less than 300 cc engines. Then I'm trying to see if you see the pollution in India, and if you look at Bangalore and Pune, they have the maximum two-wheeler density, two or three-wheeler density, and whether it is gasolines or LPG or CNGs.
So,
In North India, you have
I
seen
think now I have heard recently that some hydrogen engines are coming in the market from
yeah,
Toyota. Yeah.
three.
Yeah.
Uh, they're all for 4 cylinders, 2 liters and above.
Porcelain. Yeah,
Two
yeah.
liter.
But so what are the challenges in the small engine? Why companies are not developing small
I'll
engines?
answer it. I'll answer it. Let me answer it. One, if you look at Greaves, Aurangabad, now they have started trying to see hydrogen blended CNG engines. Okay, point number
Okay.
one.
Okay.
They have started doing it. Single cylinder engines. They're almost around 300 to 350 cc engines. They are
Okay.
doing it.
And
And
what
then
will be
second
this
thing is
blend ratio? How much blend will be there?
currently is around 4 to 6%.
4 to 6% only. Okay.
Yeah, yeah. Okay. And it takes a while. It is, and there are some works which is happening. And incidentally, a couple of months back, Bajaj Auto they have started exploring using the hydrogen for small engines.
Yeah,
Their
recently they
vehicles
also
also.
launched
Yeah,
a
correct,
CBG bike. Yeah,
correct, right. So it is not just by me doing PhD or some people doing it. We are not going to commercialize this.
yeah,
It has a humongous amount of work to be done. Humongous
true,
amount. First
true.
thing is to get rid of the mindset. See, it is if you look at in India, unfortunately, the moment you talk about this, unfortunately we have a mindset. It is not possible. First, we'll have to get out of that mindset and say yes, we can do it. Incidentally, IIT Delhi, way back in 2002 to 2004, they had run some three-wheelers using hydrogen. Okay, Mahindra three-wheelers were there. It had run. It is not that people have not explored it, but availability of hydrogen becomes another issue.
Yeah, that's the actual challenge. Now it's moving a very great speed actually in
Yeah,
every
right.
part actually. Yeah,
And at the same time, there are enough people who talk negative to hydrogen. They say, okay, India is already, we don't have enough amount of water, even though electrolysis is the best green way. If you take any scenario, 9:1 ratio in a simplistic way, we don't have water, how can we do it? There are many things which can be
yeah.
explored there.
Actually,
Many things.
so as I think I mentioned in my first introduction class, so I am also working on hydrogen production and utilization.
Yes.
So yeah, so I am exploring the way to produce hydrogen from biogas itself. Yeah. So
Yeah,
there are so
correct.
many ways to produce hydrogen. Yeah.
And if you look at just a couple of days back, since you said biogas, if you a couple of days back in China, they are planning to import cow dung across the globe and trying to use methane producing hydrogen.
Yeah, yeah,
They're planning to import, right? And a couple of years back, India were exporting cow dung to Saudi Arabia, Middle East for their agriculture purpose. And if you see the bovine population in India, how much we have, and instead of just putting them into a drain, if you try to harness that, the potential is humongous.
yeah. Right, right.
The potential is humongous. The moment the fuel is available, other things will spring up. Yeah, there is always a way to improve efficiency. That's fine. So we'll have to get that supply chain, the entire chain to be established. Things will explode. Things will definitely evolve. The best way is, as one gentleman was telling, he's in education scenario, education field for last 40 years, and he was trying to go to Canada. Yeah, there is huge potential. See,
Yeah,
there
true,
is huge
true.
potential to do it. In fact, most of you might be aware of SAE, Society of Automobile Engineers, right? I had a particular program in that for students program known as Range Extended Electric Vehicle, wherein we are trying to students, teach students about how to work with alternative fuels, exploring that. It takes a while.
Yeah,
As it says, Rome was not built over their day. It takes time. We'll have to have patience. And the issue what I'm seeing currently for my PhD work is the resources, especially the funds,
yeah.
and how
It's
to get
really
funds.
yeah,
That's the major issue. I don't know
yeah.
how to
It's
get the funds.
yeah. It's really good to know these things. So now I hope that this course will help you a lot because you are also doing PhD on hydrogen itself. So I think the concept that you learned during this course will be very useful for you in your PhD.
Yeah,
Yeah.
correct. And since
Can
I'm
your
working at this issue. Sorry.
sir, can you please give your mobile number, please, sir? We will get in touch with us so that we can work in this angle. Sir, your
Yeah.
name,
So
You
please.
can just note down. You can
yeah,
note down.
please don't mention your mobile number over because this meeting is being recorded and it will
Okay,
be
sir.
put
No,
on online. So it's better way that you can either use message box, okay, or
okay, sir. Okay.
the course form you can use that. So that will be a better option for this. Okay.
Thank you, sir.
So
Thank
thank
you,
you
sir.
for sharing your
Can
thoughts.
can you repeat your good name? The gentleman
Sir,
said.
I am Dr. S. Shanmugam.
Oh, okay, right.
I am
You are from?
S. Shanmugam, worked in steel industry for about 40 years. Of Government of
Oh,
India,
super.
State, Finland,
Okay,
SAIL. I retired
okay,
as a assistant in mechanical maintenance. Then
okay.
because
Excellent.
I'm doing some
Then you know the safety aspects pretty much well. You will be
yes,
in
yes.
depth of safety there.
I'm expert
So
in
yeah,
safety.
maybe you can both connect over LinkedIn, and yeah, you can share your details, and you can have a good meeting later on.
Right?
And
Yeah, sure.
yeah, I
We'll
think
do
you
that.
can both help each other. Yeah, yeah. Thank you.
Thank you.
Correct.
Thank you very much.
Thank you. Yeah,
Thank
next
you.
please. Yeah, next. So Hitesh, do you want to share something?
Yeah,
Yeah,
yeah, Mr. Amit. Actually, I'm working in a power plant, gas-based power plant. So I joined this course that in the future there will be some hydrogen will be blended with the natural gas. So
yeah,
that
right.
future will be I'm forecasting. Maybe the government is already started in the city gas distribution also. So for the gaining of the knowledge, I joined this course. So I gained a lot of knowledge from the basic from the hydrogen properties to up to how the different methods of production, how to we have to handle, and mostly there is a safety aspect also. So the thank you very much, Pratibha ma'am, and you also, and so thank you very much for their class.
Yeah, thank you, thank you. I hope this course will help you a lot in your future projects. Thank you, Hitesh.
Yeah.
Thank you. Yeah, Asim.
Yeah. So good evening, everybody, and happy Dashera. Yeah.
Yeah, same to
Uh,
you.
yeah. So I am working as a consultant, and I have about 22 years experience. My career has started with working in especially in power projects. Okay. So I am graduate from Jadavpur University as power plant engineer. Then I did my master degree from IIT Delhi in energy and environment management. Okay,
Okay.
and mostly I worked in consultancy, and they are now the in thermal power plants, those are energy transition is happening. So we are doing now the renewable energy, different kind of renewable energy, of course, the solar, then wind, then hybrid, then energy storage like battery storage systems, those things. Okay. And hydrogen generation, yes, I did from my initial stage of my career. You must be knowing in each power plant, mostly which are in remote location. So there are small hydrogen generator. So, and that was through also this, mostly I have seen that through this electrolytic process. Though that time I knew that, I mean, about this hydrogen, only the superficial knowledge was there.
Okay.
Now two more and more projects are coming. We are also as a consultant getting inquiry on that. Okay, so you can say I have started this thing to as a skill development in this field. So that in the whole energy scenario or energy transition, I can be in the position of, myself in this field.
Yeah, good,
Okay.
good. Nice to hear this. Yeah. So I hope,
Yeah.
yeah. So I hope you will you have gained so much of knowledge from this course, and
Yeah. Yeah.
explore this. Yeah,
And
and you can
and
share
and
this with
I
your clients. Yeah, yeah.
Yes. And from last year only, I am also I wrote Pratibha ma'am also where when you are starting this course. Okay, so she wrote me also. So I
Okay.
found you people all were those, including Pratibha ma'am. So everybody were responsive. I mean, any question we put, we get the response very quickly, and so that is good thing in this course. What we are fine. Now I have few one or two very small question regarding water. So we need a lot of water in hydrogen, and that water quality also, it's very say it is not even dimine water, and it will be more than purity will be more than the dimine water. What I understand.
Okay.
So yeah, so the dimming water also, I have experience in in the consultancy, uh, as well as so the requirement in the field will be in different way. Like in this water production also, this water will not be simple water. So water production industry also will grow.
Yeah, right, right, right.
Yes, yeah. So yeah, and. I have one question that regarding the green hydrogen. So what I understand from this course that only the hydrogen generation through the electrolysis process is the only way for to get the green hydrogen. Am I
No,
correct?
no. So hydrogen produced from the renewable energy is considered as a green hydrogen. Okay. So the
Mhm.
one way is the electrolysis, and other way is also like you can use the biogas or like any. So in if you are using the biogas, then there will be some CO2 emission will be there, but that will be the biogenic CO2. So there is so that CO2 will be like you can consider is the neutral. So that also considered as the green hydrogen, and there is a much more definition about this. So recently, MNRE shared like a proper definition of green hydrogen. So you can just Google it, the definition of green hydrogen by MNRE. So you will have more knowledge about this. So basically, from the whole process, if you are emitting 2 kg of CO2 per kg of hydrogen, that is also considered as the green hydrogen. Okay, so
Okay.
yeah, in every process there should be the maximum limit is 2 kg of CO2 per kg of hydrogen. And yes, yeah, so you can go through the definition. So biomass is also, if you are using the biomass and also producing the hydrogen,
Mhm.
that is
Okay.
also considered the green hydrogen. But the thing is
Okay.
that the emission of CO2.
Okay, okay.
Yeah,
Okay, so I understand. I understand. Recently I am doing a project which we are in the industry, especially in the power industry. We are assessing how much green hydrogen greenhouse gas is being releasing, and we are doing the energy efficiency also, and by that way, how much we can reduce. Okay,
oh
by
nice.
installing different options. Uh, Second question is on fuel cell versus IC engine, which is going to dominate the transport sector. Basically, that is my
So
because
yeah,
it was not concluded in the course.
yeah.
What I can.
So actually, it depends on so many scenarios. So if you compare the aspect of efficiency, then fuel cell is performing far better than the IC engine. Okay, but the thing is the cost. So that is the thing. So maybe if the cost of fuel cell is like it comes down drastically in like upcoming years, then yeah, it can dominate. But also the companies are also working toward the hydrogen engines also. So that's also having a good competition. So let's see. Only future can tell actually which one is going to win. So yeah,
Oh, yeah.
both of these technology have their own benefits actually. Yeah. So because
Okay.
engines, we know that they are already we are using those for decades, and with the some improvement we can use the hydrogen in that. So that's also a part. But fuel cell is a different kind, different thing. So it depend actually. Yeah. So let's see. Only future
Yes. Yes.
holds this answer. Yeah.
Yeah,
Okay.
thank
Thank you.
you. Yeah,
Thank
thank
you
you,
for
and
sharing
thank
your thoughts. Yeah.
all of my, colleagues here. Okay, so we can have talks with each other
Yeah.
because
Sure.
during
Sure.
the course also we had some connection. We replied many questions, asked questions. Okay, so that in future it will be winning for all of us.
Yeah.
We will try to contact everybody. I mean, if required. Okay, so
Yeah.
thanks
Thank you.
all.
Thank you, Shim, for sharing your thoughts. Thank you. Yeah, so next, quickly, just brief. So, Mukesh, I think you have done already, Mukesh. Mithun,
Yeah, good evening, sir.
yeah,
It's okay, sir. Nice interacting with you and other people. And it's basically a good course. So let me think, let me carry forward this what I can. Yeah,
yeah,
thank you so much.
thank you. So, I hope this course will help you a lot, and whatever you want to do in the hydrogen research. So, yeah, I think it will help you. Thank you, Mithun. So, Jayaprakash,
Hi,
Mr. Jayaprakash, yeah, hi, hi,
uh, good evening to all. I'm basically an electrical engineer having more than 30 years of experience, mainly in alkali and petrochemical and refineries. Although I was aware of the hydrogen production systems and all, I have used that. After my superannuation, I am working as a consultant in solar energy power generation, being an electrical engineer. I wanted to integrate hydrogen with the solar plant.
Okay.
So my intent was to understand detail hydrogen. I was aware of the user hazards, everything of hydrogen, but to other properties also. So this course given a lot of new learnings, new things, interacting with so many persons. I've interacted with Pratibha ma'am also during my Delhi. I was in Delhi. Some MNRE meet was there last month,
Yeah, yeah.
where
So
she
there
has
was a
participated.
conference. Yeah, yeah, yeah.
Yeah, she has come. So a lot of new things I have learned. I want to apply, integrate these hydrogen as well as solar energy for the
Yeah.
energy generation, for transportation, other which may be the economical process. So in that way, a lot learned me a lot. Although I have done 2 3 courses in renewable energy field through NTPTEL, where the hydrogen part was very little touched. So this
Yeah, yeah.
course has given me a good breakdown, good background. So, so it was a very sincere effort of you also to summarize all the things, a very good language and very polite way.
Thank
It's
you.
a very nice thing.
Yeah,
Yeah.
thank you.
Thank you. Yeah. Thanks.
Yeah, thank you. I hope this course will help you a lot in your future, like
Yeah.
integration
Yeah.
of solar
Definitely.
energy to the
Definitely.
hydrogen production. Yeah,
Yes. Yes.
yeah.
Thank you.
Thank you. Thank you. So next, YN, I think you know your name
Good
is not.
evening, sir.
Yeah,
This
yeah.
is
Hi.
Mr. from Nategar.
Yeah.
I have missed couple of classes. In fact, this is a second interaction that I am participating, but
Okay.
nonetheless, it has been very informative and very structured course content. I was really impressed by the quantum of methodical information as well as the problems that were offered as a part of the learning part, which gave a good deal of insight into the various aspects of the systems and the design, the standards as such. Well, we are actually working in the hydrogen space and the renewable space. So we are into renewable energy generation, hybrid energy solutions. We have been exporting long duration energy storage systems to US and other
Okay. Nice.
markets. I think last time I had mentioned that we already commissioned a hydrogen fueling station in Faridabad for IOCL.
Yeah, yeah. I
So
think yeah,
that
yeah.
was
You mentioned yeah, yeah, yeah,
So I think that is area of interest to you because you want it from CBG route or natural gas route.
yeah.
So there we are already deployed that. It is for the hydrogen fueling station. So for the long distance transportation trials which are going on for some Tata buses and all. So it meets the Society of Automobile Industry standards and all which are required for that. Currently, we are working on uh, design of CBG plants for different feedstocks. We are in advanced stage of certain this, essentially to backward integrate our solutions to produce hydrogen from CBG, essentially.
Yeah.
We have also
Nice.
started working on the green hydrogen plant for one of the major industry, and possibly that would be one of the major green hydrogen plant for in India. So we are already into the design phase of that. So
Oh, nice, nice.
uh,
So you
we,
are working a lot in this sector actually. Yeah.
yeah, that's one of the reason that I couldn't attend many of the courses, though I wanted to attend it, but the travel and a lot of other pressures are
Yeah.
priority currently.
Yeah.
We
Yeah.
are
Right.
looking for some good young engineers in case there are some people whom you can suggest and send us the resumes. That
So
would
you
be
you
a great
can you
help.
can you can email me. So yeah, yeah. Maybe I
Definitely, sir.
can help you in this. So you have my email ID. So just email
Right,
me
right.
your email because I don't have your contact details. So just share your details. So I will be in touch. Yeah.
I shall drop you an email. Yeah.
Yeah. Yeah. Sure.
So yeah,
Sure.
it was yeah much thankful to Pratibha madam and you as well as the rest of the team members who have been working very hard to put in this kind of a course material. This is like excellent getting this kind of information on one sort of course or sessions like 12. I'm still trying to catch up. I'm on the week 4, 5.
Actually, yeah,
Hope
it's a
I'll
good
have the
thing that everything is recorded. So yeah, you can go through the videos. Yeah.
yeah. I hope the this will not be locked up. I'll have the access for some time. So
Yeah.
next
You
couple
will
of
have access. You will have access. I think. Yeah, you will have
yeah.
access. Don't worry.
I hope to catch up during the Diwali vacation. So that's what I'm looking forward to because
Yeah.
there's a lot of other activities keeping things
Yeah.
bit occupied. But
Yeah.
thank you once
Nice.
again, and thanks to
Yeah.
all the
Thank you.
other participants for their lovely interaction during this session. And I think we can form a small group as a part of this outside the WhatsApp group or whatever. So we
Yeah.
can continue
So
with
yeah,
our
yeah. If you are forming any group, so you can also share the details to me. So yeah, I'm also happy to join. Yeah.
sure, sure.
Yeah.
I'll drop you a mail and then we can initiate this because I think you'll have much of the phone numbers through the
Yeah.
so,
Sure. Sure.
I think that could be the way we can interact.
Yeah.
And if there
Sure.
are any such programs coming up in the future, like please let us know. We'll be happy to also induct some of our people onto this kind of a program. And
So this
thanks once
course is
again.
like is happening I think every semester. So
Okay,
if you want to like connect this course with your colleagues, so yeah, you can refer them. I think it's now yeah, maybe in January or I think in Feb there will be another
perfect.
course. Yeah, so you can
Actually,
explore that. Yeah,
right. I live just across IIT Mumbai campus, so IIT Powai. I mean here in Hirandani, so it's just about a
nice.
walking distance.
Yeah,
So we look forward to meeting you in person as well, sir. Thanks for
yeah.
all the
Actually,
support.
yeah, I am at IIT Delhi, so I am from IIT Delhi.
Okay,
So to meet
I
me, you
can
have to come to Delhi. Yeah.
definitely. Delhi is like every second week we are hopping to Delhi for some or other
Yeah,
job.
so just drop
So
an email to me. Yeah. We can also have a meeting, no issue. Yeah. Because I'm also
absolutely, yeah.
working in this domain, so yeah, we can have a meeting, no issue.
Right.
Yeah,
Look forward to continue
yeah,
with this
sure.
interaction.
Yeah.
Thank you.
Thank you.
Good.
Thank you sharing this. Yeah. Next, I think Vivek, Mr. Vivek.
Uh,
Yeah,
yes.
yeah, hi.
So I'm Vivek. Actually, I have attended 3-4 classes of this. I am a mechanical engineer and in Cummins India Limited, working almost 18 years now in the diesel engines. So I was looking for this course. I was just tracking. I missed the this year's first semester course, but I was tracking to join as soon as the nominations were open. I joined this course, and this was my first NPTEL online course, and this is a very good way of teaching the live lections as well as the uh, summarized week sessions by you for these 2 hours. And your method especially is very good. You are explaining first the problem and then the associated lecture slides. That is also a good way of things. And one more motto was connecting into this, coming into this field, connecting networks. I was connecting the people on the LinkedIn as well, and I would like to connect all of you also in that group if that
Yeah,
form. So overall, good experience learning. Thank you.
yeah. Thank you. Thank you, Mr. Vivek, for sharing this, and I hope this course will help you in your future projects and comments. Thank you.
Yeah, sure.
Yeah, thank you. So anybody else?
Amit, is
Yeah,
it
hi.
will possible for one revision lecture? Other courses are being done like that
Yeah,
through
actually,
NPTEL.
yeah. So actually, yeah, for this, I'm not taking any further classes. So maybe the other the other tutor. So maybe he's having a revision class, so you can explore that. So from my end, so today is the last class. So because I have some other engagement with me, so yeah, I'm not able to take the revision class. So, but still, if you have any doubt, so you can email me. No issue. I'm happy to answer your queries after this class also. So you all have my email ID, my LinkedIn ID. So those who want to connect, just send me an email or share your LinkedIn. So yeah, I'm happy to connect. So anybody left?
Yeah, hi. This is Gulab Chand Gupta.
Yeah.
Uh,
Please.
yeah, I am into water and wastewater background. So I'm having completed 20 plus years of experience in design and engineering of water and wastewater. So I have came across so many times about green hydrogen, green hydrogen. So I wanted to just explore what exactly is into. So while joining this course, I had already attended almost all the courses. The last week course I am just having, means I need to attend. So I'm going through it. So I would say my experience was a very good experience. The way the lecture has been means organized, I had came to know more and more about hydrogen, not only green hydrogen. What are the other types of hydrogen, and the production as well as transportation, then storage, and the safety. It is very good way that the team has presented to the complete team. Okay, so I'm really impressed and would like to go through other courses which are relevant to my field, and would also like to means see which would be the there are various water treatment required for the hydrogen generation with respect to the green hydrogen field. So I would like to explore that even.
Yeah,
And
nice,
thank you
nice.
to you and your explanation also, as everyone said. I would also like to tell that the way of explanation was very good. It was a very nice way to understand all the subject. And someone has also asked about the group formation. We had already formed a WhatsApp group and we are into it. So most of the people, they used to share their queries in that group and we used to get the solution out of it.
Yeah, please share that group invite to my email. So I'm also happy to join. Yeah, that group. Yeah,
Yeah, sure.
yeah, sure, sure.
Even we would like to join. Somehow we can't share that. Somehow
Same here.
if we can get it, yeah, we would like to join
Yeah,
that. Thanks for
yeah.
that.
Sure.
Thank you, Mr. Gulabchand. So thank you for
Yeah, thank
sharing your experience, and I hope this course knowledge will help you to like work more on this water treatment projects, and maybe you can also explore the green hydrogen way. Yeah, thank you.
Yeah, sure. Thank you.
So anybody else?
So, so can you just repeat his
I
name,
think
Gulab Chand?
every yeah, it's Mr.
Gulabchan
Gulabchand
Gupta.
Gupta. Yeah.
Okay, I'm trying to ping you on the LinkedIn. Then. Okay.
Okay. Okay. So is anybody left? Okay. So thank you everyone. Thank you everyone for joining. I think you all attended my every session, I think. So almost every session. So thank you for joining every session. So I hope I helped you a lot. So I try to like communicate with you and try to like interact with you and also have discussion. So all the best for your future endeavors, and I hope this course will help you a lot in your future projects, learning, research, and whatever you want to do. Okay, so thank you.
Thank you, sir.
Yeah, thank you.
Thank you.
So you all have my email ID and my LinkedIn ID. So those who
Can you
want to
flash
connect,
once again?
yeah. Sorry.
Can you flash once again the last slide?
Yeah, just let me once again. So yeah, in every PPT also, so my ID is there. So you can also check there, no issue. Yeah. So and if you are coming to Delhi, so you just drop an email. We can plan a meeting also if you want to discuss more about the hydrogen. Yeah.
Okay, thank you.
Sure, sir. Look forward to meet you in Delhi soon.
Yeah, sure, sure. Okay.
Good day.
Thank you.
Thank you.
Thank you everyone. Bye bye.
Bye.
Yeah.
Bye bye.
Thank you.